Hi everybody. Thanks for having me. This is a great workshop, this kind of idea of bringing databases and machine learning together and thinking about what databases and database technology can do for machine learning. So I wanted to talk today about this idea of a data curation and debugging for what's called data-centric AI. And this is work of a lot of people that work together, collaborate with me. We'll come back to them during the talk and I'll tell you who they are while we talk. So the thing I wanted to start out with is to think a little bit about the importance of data, right? So, and I'm going to do that by just saying, here's a podcast recommendation. So this is a podcast called 99% Invisible, great little podcast. And they had a podcast last week about the importance of data tracking in the United States in the pandemic and how it's really difficult actually to create, for example, the statistics needed to track the progression of COVID. So if you're interested in how data is made and really the boots on the ground of actually creating data sets, this is a fantastic podcast. And I think this is kind of the central idea that we're getting to with data-centric AI, is that we're realizing more and more the importance of creating data, of the process of making data, and its vital importance. And I think we've known that for a lot of domains, but we're realizing it again and again in the area of machine learning. And you can see that in these kind of more high-level perspective views. So here's one from The Economist, where it says, finding digital truth, identifying, combining data that accurately represents reality. And this is getting more difficult. And this is really important because a firm needs to get their data house in order to benefit from AI. And likewise, the European Commission talks about the importance of data interoperability and quality, and that data is key for the exploitation of data value, especially in the context of AI deployments. So this is, again, the idea that the making of data is valuable. And I think oftentimes we know this statistic, right? That, the making of data is actually really hard, right? And you have all sorts of these ideas of data scientists spending a majority of their time, cleaning, munging, managing data, moving data, and really less time actually building new models. And I think this awareness has really come into fore under this theme in the machine learning area, under this idea of data-centric AI. You may also have heard of this under another name. It's called Software 2.0, was another name before this. And this is really the idea that you have really two parts when you build an AI system, right? You have the code, right? The model making, and you have the data itself. And what data-centric AI is about is how can we essentially systematically change our data to help improve performance, and really making machine learning operations tools or data science tools that are really focused on making high quality data available throughout the whole machine learning project lifecycle. So this is actually the kind of maybe the talk in data-centric AI, really branding it in some sense by Andrew Ng. And so I suggest you actually go listen to that talk. But this is the fundamental idea behind data-centric AI. And maybe this is a rebranding in some sense of other notions that we've been talking about in the data science community about the importance of data, about making of data, and about the difficulty in doing that and the making of that. But I think it's really an important shift to really say, okay, without good quality data, we won't have good quality data. And when I look at the shape of when we think about why this is challenging, why is it so challenging to make new AI systems and build good quality data is these three things. For me, it's a lot of stuff we do is manual, right? So we still work in Jupyter notebooks, we still do a lot of copying and pasting, we still email each other data sets, our annotations are sometimes done manually. So there's still a lot of manual practices in our data science and AI practice. It's oftentimes hard to really reuse workflows, right? So you figure out how to build a new recommender system model. How can I reuse that in a completely new context with different data sets or different environments? So there's this difficulty in creating reusable workflows that are flexible to different tasks. And finally, there's sometimes a lack of transparency. Now, I think this is getting dealt with more and more in the machine learning community with things like parameter servers or systems where we can actually track what's going on during training. But I still think there's a lack of transparency throughout the entire machine learning workflow, data science workflow, in particular when we think about things like data integration, data preparation, and sourcing of data. So I would claim that these are kind of the three big bottlenecks. And what I want to talk to you about is some work we've been doing to try to, really address some of these things, in particular around transparency and about making things more automated. And I want to do that in two different contexts. So the first is debugging. And this is work really done by Stefan and in collaboration with Sebastian and Julia. And this is work really thinking about this problem of how do we debug, how do we figure out what's going on in the data pre-processing pipelines of machine learning systems. So let me give you an example. So if we look at an ML pipeline in the real world, what you have is you usually have heterogeneous data sources, and they may be stored in all sorts of systems, right? So you may have it in an S3 buckets, you may have it in a BigQuery template or stored in Delta Lake. You do some integration and cleaning, right? So you'll probably do that in something like Pandas. Maybe you're using Apache Spark to do that. You'll put all that together. You'll get this lovely data frame, which has your which has the features of your data kind of cleaned up to train your machine learning model. You'll do some feature augmentation or feature encoding. Maybe you'll do some data augmentation to that pipeline. And then finally, you'll train it with a different set of tools, right? Here you're thinking about things like TensorFlow and PyTorch. So this is kind of a perspective on what a ML pipeline would look like in the real world. Now, all sorts of problems can occur in this kind of pipeline, right? So the first one, you might have data representation bugs, right? So you might not have the right set of people in your data set itself. You might have in the feature encoding pipelines, or you might have missing data, right? Or you might violate particular schemas that you have. So that might be an error that happens. You might have an on-sound experimentation, and this is actually quite challenging, right? So you might have data leakage across training and test sets, things like that. And this happens quite a lot, actually. And you have to be very careful about how you set up your training, validation, and test sets in a machine learning pipeline. So you have all these different bugs that can arise in the machine learning pipelines, and it would be good to have tools that help you figure out if those bugs are there. Stefan and Sebastian started thinking about a kind of a new way forward to recognizing those bugs and helping data scientists and machine learning practitioners address them. So one approach you could have is to invent entirely new programming languages and runtime systems, right? This is great, right? So if you get everybody into a single system, you could do lots of things, right? But the problem is that we live in a heterogeneous world lots of different stacks that people build on, lots of different different tools for different parts of the pipelines. Another approach, which is an approach that's I kind of pursued in some of my provenance work, was to kind of manually annotate and instrument existing code, right? So if you can have people kind of instrument their code correctly, then you can record this information and be able to debug in practice. It turns out that this doesn't happen, right? So people are very reticent to actually instrument their code or do a lot of manual annotation. So the idea that Sebastian and Stefan had was to retrofit inspection techniques into the existing data science landscape. So the key observation here was that, especially for operations about pre-processing, there's kind of a couple different packages that are already used, namely pandas, right? So people put things in a pandas data frame. They do a lot of joining and merging and filtering in using pandas. And there's this kind of pipeline when you're training your machine learning models in scikit-learn, or if you look at TensorFlow, they use these kind of declaratively specified transformation pipelines. So if we focus on these kind of commonly used packages, we can kind of bridge the two worlds, right? We can automatically instrument without forcing people to adopt an entirely new program language and runtime system. So let me give you an example of what we're talking about here, a little bit more specific. So this is an example from the healthcare domain of a workflow you might like to run, or a machine learning pipeline. So you have some patient data, you have some history data, and what you see on the left side here is you see potential issues that could occur, right? So what we do here is we join this data about patients and their histories on an ID, social security number essentially, and this join actually might change the proportions of groups in your data, right? Now what we're going to do is do some processing, so you can compute the mean complications per age group, and you're going to add that as a column, right? Then we're going to figure out the target variable of the data sets, and then what we're going to do is project the data, right? So it's just a munging of the data, and we're going to filter by countries. Now, when you project out this data, right, we're not going to use this age group, but that age group data, age group column, might be important for calculating whether you're fair or not in the data set. Then what we're going down to is we're going to select the data by a country, and that selection might also change the proportions of groups in your data, right? By taking out, for example, the Netherlands or the US. Now there might be some missing data, right? So you perform some imputation with scikit-learn, and that imputation may again change the proportions of groups in your data. And then here what you see is that you're training on whether you're a smoker, what country you're from, but you're also training on race. So this might have fairness implications, right? You might not be able to use race as a factor in creating your machine learning model in legally. And here we also embed the last name of the person, and embedding vectors may not be available for particular names, right? And then we go ahead and train a model, right, on this to kind of predict potential issues with the people. And so the point here is these errors may arise, or these data problems, may occur in your workflow. So can we find ways of automatically hinting to data science at potential problematic operations. And the kind of inspiration here is if you think about code inspection in a modern IDE, right? You're programming along and you do an error, it pops up, it says, hey, this might not be okay. So this is kind of the idea behind what we're doing. So to address this, the idea was, okay, we have this code, but we need an abstract representation of this code. So what we do is we go through and we actually generate a DAG of the data flow through that code, right? And this allows us to look at the same kinds of code and build this abstract representation on the left side, right? So you see that's a join, you see there's a project, so kind of standard database mechanisms. You see a split, you see the embeddings, and you see the encode. And now what we can do is we can write over this data flow DAG, we can write detectors on top of that data flow DAG to see if we can find those potential problems. And this is the tool ML Inspect. So what we can do is instrument this ML pre-processing code with custom inspections. It's available in open source. And the important point here is that we work with native pre-processing pipelines. So you can see on the left side what a pipeline inspector looks like. Essentially, all you have to do is you put this pipeline inspector on the original Python code. So you don't change your code at all. And then you add these inspections, right? So did you introduce bias? Are there no missing embeddings? Do you have illegal features? Did you introduce bias for these two columns? And the important thing here is that we're not you don't have to do anything to your original Python code. What we're doing is monkey patching. So actually inline editing the Python code that you produce with the instrumentation that we need in order to actually do these detections, right? To generate the corresponding DAG and then analyze that DAG. Here you can implement the inspections as user-defined functions, and they'll automatically be applied to all the inputs and outputs of particular operations you define. So this is a very cool thing, right? So we can extensively instrument our code without having to actually change it, with this assumption about the structure of something like pandas and scikit-learn. So here's an example of a couple of those inspections. First is lineage tracking or provenance tracking. And what we can do is automatically identify annotations for particular records and propagate them directly through as those records are changed, right? So here we have a join, right? And in classic provenance polynomial style, what we can do is we can say, okay, we're joining on social security numbers, so we join this row and join this row, and you have a joined row, and we can see that that annotation comes from P1 and C1, right? And then what we can do is we can select out or project out two columns, right? And then we maintain all the original rows that this came from. And this lets you address these things like, okay, am I excluding different proportions of the population that I should or shouldn't have, right? Or in this example where we were talking about the need to keep track of the age group, right? We can go back and track through the provenance record which age groups were involved. Similarly, we can see if if there are changes between proportions of projected groups or protected groups after we do some sort of selection. Here we do projection on country, and we can essentially see by comparing those two things the change in distribution on that age group variable. So these are the kinds of inspections that you can create, and they're simpler to create because you have this abstract representation as a DAG. So that was ML specs for debugging. So it's a general runtime for ML pipelines analysis. You can get it on GitHub. I think the main limitation, but also the success of this, is that it really relies on these declaratively written ML pipelines in something like pandas and scikit-learn, where we can actually identify the semantics of the operations there. And it enables a bunch of different kinds of use case. A cool one that Sebastian recently did was Argus Eyes, which is a CI tool, a continuous integration tool that uses the ML inspect to help you kind of detect these errors as you change your ML pipeline. So that was data debugging. Now I want to talk about data curation. So here, this is first set of work is with Laura Costin, Pavlos, and Professor Elena Semprell from KCL. And then I'll talk about a separate set of work with Madeline Halsebus and Chartai from Sigma Computing. So a question that we had was, what curation for these machine learning pipelines, or in general pipelines, should data providers prioritize to facilitate data reuse? So I have this data sets in my data lake, or I'm posting on the web, or I'm providing, what kinds of curation should I do first, right? And there's actually a lot of good advice, right? On, hey, here's how you should curate data set. Here's what metadata you should add to actually make your data more reusable for other people. And I'm guilty of writing this advice myself. So here are two papers. One, 10 simple rules for the care and feeding of data. The other one is the FAIR guiding principles for scientific data management. So advice on how you should curate your data. And in fact, there's a lot of advice, right? So if you go to fairsharing.org, there are about 140 different policies on how you should kind of add metadata to your data sets to make them available for reuse. We reviewed 40 papers in the literature in this particular article with all sorts of advice, and we cataloged about 40 different features of data sets that, according to the literature, enable effective data reuse. Now, if you spent all your time doing all this metadata addition, it would be a lot of work, right? So what should we prioritize, right? If we're trying to provide data for people to reuse it for their machine learning applications or their analytics applications in general, what should we do, right? And for me, it was a bit overwhelming, right? And I think for a lot of people, it's overwhelming. So could we prioritize this advice? So here we do a trick that I think is really interesting, is we look at publicly available data. And in particular, we look at GitHub. And we took 1.4 million data sets. And by data set here, we mean either a CSV file or an Excel file from about 60,000, 65,000 repositories. And then what we said was, we need a way of measuring data reuse. So are people reusing this data? And we used engagement metrics as proxies for data. So you can look at things like contributors, you can think of things like stars or forks or watches as ways of kind of engagement with the data sets and kind of a proxy for whether people will reuse it or not. And then what we did was we mapped the features of the literature onto GitHub repository features. So those 39 features that I were talking about, we kind of connected those to features that you would see in GitHub. And then what we were trying to do is train a predictive model to see what features, right? What of these data reuse features or these metadata features are good predictors of data reuse. So what do we mean by data set features, right? So you could think of things like how many columns and rows are there in a data set? What's the size of the data set? Are there missing values in the data set? Then you have more kind of metadata about the data set. What are issues, right, on the data set? Is there a description of the data set? can you parse the actual data set? How old is the data set? And how good is the README? So features about the README documentation. So these are all features of the data set. And the question is, which of these features should make it more reusable, right? That's what we're trying to answer here. And this would be a guide as to where you should focus, right? If you want to make your data set more reusable, how you want to curate your data. So we did this. We trained a machine learning model on this to kind of predict these proxy reuse measures. And you see some decent performance, right? So if we look at the kinds of features, if you just look at the data set itself, okay, you get 49%. If you just look at the description, you get 42%. And as we add more features, you get better in performance on actually predicting whether a data set would be reused. Now, the key point here is not to think about this in terms of how good are we at predicting data set reuse, but can this help us distinguish which features that you should focus on in order to create data reuse? So it's always hard to really perfectly predict whether a data set will be reused or not. But what we can do is by looking at the various features, what to concentrate on. And so for us, what we saw was that if you're going to provide a published data, right, a thing to focus on is provide in short textual summaries, right? This actually helps with performance. Provide comprehensive README file. This kind of makes sense, right? But maybe that's the first thing you should do. Another interesting one I found was that there's, if you have too big of a data sets, right, these become harder to reuse. So don't exceed standard processable file sizes. And the last one is make sure your data sets are actually open in pandas, right? So this is something that we saw all the time. If you can't open it in a tool that people normally use, then you get less reuse. So this is how we should prioritize curating our data sets for reuse. How am I doing on time?
You still have 10 minutes, I would say.
Yeah. Perfect. Great. So on this topic of curation, can we help automate curation? And so this is work by Madeline, who's here, about what we call Git tables, which is a large-scale corpus of relational tables. And I think the motivation for this work comes from this idea of how do we help automate some of the creation about relational tables. And so I'll give you an example of a kind of task you would want to do to curate a data set, specifically semantic column type detection, right? So you're given a data set and you're given different column names, right? And so what you want to do in semantic column type detection is map these column names into common types from a ontology or vocabulary that you're given. So for example, we want to know writer ID is an ID from an ontology like DBpedia or schema.org, or that this age with the uppercase is actually age as defined in ontology. And column type detection is super useful for all sorts of things. One place it's useful for is data integration, right? So you know you could join two possible columns, right? So if somebody uses rating in one and rating in another, we know they're the same. You can more easily do a join. And so that's an example of something that you could do with semantic column type detection. And Madeline will correct me if I'm wrong. She's here. I think she built kind of one of the state-of-the-art in semantic type detection for table columns in 2019. And I think there, the key idea was, okay, we're training these column type detectors on web data, right? Particular web tables. And then the question is that the kind of data to help us build the best column to type detector or the best automatic curation system for relational tables? tables that you more commonly see in a data lake, for example. And for these kinds of tools, for machine learning tools that do this automatic creation, you need table corpora. And in general, corpora have been really important in a lot of different domains. So from understanding images in natural languages, you need data sets. Likewise, to understand tables, you need annotated data sets. And the annotated data sets, or the data sets that we've had for tables, have primarily come from the web. So you can think about the canonical work in the space, web tables, right? Back from 2008, there's newer versions called wiki tables, but pretty much every one of these table corpora is sourced from the web. And what we found is that these data sets don't really look like what you find in a relational database, right? So what we wanted as a new corpora with database-like table content and structure, right? The same kinds of semantics you see in a relational table, the same kind of data types, similar sizes. We wanted it to be big enough so these methods right here, understanding images or natural language, require a lot of data, right? So we wanted a corpora that wasn't small, that was large enough to build representation, to do representation learning on. We wanted it from a diversity of domains. And we wanted some sort of annotations where we can do things like table semantics or do this kind of column type prediction, for example. So again, we turn towards CSVs from GitHub, right? So I'm not going to tell you the whole very complicated data engineering process of building this corpora. You can find a lot of more details at gettables.github.io. It's a lot of work, but this corpus is a little bit different from what you get in the standard corpora available for tables sourced from the web. So you can see that the average number of rows is much longer, right? So you have many more rows. So 142 versus web tables that are around 11 or 17. Likewise, the average number of columns, right, is more. So you about double the number of columns as a web table corpus. Also, we see when we do statistics is that the kinds of columns that you have, right? So for example, the column ID, very common in relational tables and very common from CSVs from GitHub. But ID, the column name ID, doesn't really appear very high frequently on these web table corpus. So what you have here is a different table or a different table corpora that we're building out from currently 1 million going up that look more like relational tables. And you can see that when you actually go and train, for example, these semantic type detection models, you get different performance when you train on these different corpus, which is kind of to be expected, but really tells you the need for a different corpora. So if you look at training these type detection models, if we train on Visnet, right, and we evaluate on Git tables, the macro F1 score is about 10% lower, or about 10 points lower than the F1 score if we just train on Visnet and test on Visnet, right? So very different performance scores when you train on web table or on Git tables versus web tables, which gives you an indication that it's good to have a different set of corpora to actually train these new models. So I think there's a lot of opportunities, or we think there's a lot of opportunities here. Many more tables, right? So GitHub itself has 92 million CSVs. We have currently 1 million. We have our data engineering pipeline running, and we hope to get about 10 million tables. We would like to annotate Git tables more with enterprise ontologies. Currently, we annotate it with for semantic types with the DBPD ontology and the schema.org ontology. Could we do enhancements on knowledge bases with Git tables? So can we use the actual data that we're getting from Git tables to actually build out knowledge bases or knowledge graphs? And whatever you think, right? Are there other use cases that benefit from this corpus? So when we think about curating data, there's often the need for new data sets that allow us to train these automatic models. And I think Git tables is our attempt at making that data set available to create these better semantic type detection models, for example. All right, so I've talked to you about data debugging. I've talked to you about thinking about data curation in this space, prioritizing where we should put manual effort in data curation, and also building the kind of backbone to train models that let us do automatic curation. And in general, I think there's this need to think about how we can make tools that improve data supply chains, right? And I think this is a key thing to creating data-centric AI, right? Given the central challenge of sharing data, we need to think more about what I like to call fair trade data. Can we give quality stamps to data sets that show how where the data comes from, its provenance, and also where we can use it and effectively use it to create the kind of high quality data that's needed to make really good machine learning models. So this notion of fair trade that we have for our coffee, we should apply it as well to our data sets. And with that, just to wrap up, AI is data centric, right? It's what we do here in a database conference or a data management conference is really important to the future of AI. We need tools that help users to debug and curate their data for machine learning. And I think the way forward is really the conversation that this workshop is about, this conversation between machine learning and database research communities, but as well as the HCI research community. So thinking about how we integrate people into the whole pipeline of ML ops in general. And with that, I'll take some questions.
Thank you very much, Paul, for the very interesting talk. Are there any questions in the audience? If so, you can raise your hand and then I can unmute you. Or maybe just type your question in the chat. So let me start with a question that I have about ML Inspect. So I am a fan of the tool. I think it's really easy to use to get all this interesting information from the machine learning pipeline. I was wondering a bit about the overhead, if there is any, on the execution time of the pipeline by having this instrumented code. For example, when we also want to track the lineage for every record, could you elaborate a bit more on the scalability of this? Are there any low-hanging fruits for improvement there if the scalability is not great nowadays?
So I think there's two things to say there. In these machine learning pipelines, one of the things to note is that the time for the whole pipeline is just completely dominated by the training of the model, right? So all the instrumentation we do in the pre-processing, all that tracking, is if you include the time of the actual training of the model, even if it's more expensive, it just kind of disappears, right? So that's the first thing to say, right? So machine learning training is just expensive, so it dominates the rest. So yes, there is overheads in the actual tracking of itself, And I think there, what we've been looking about is, because now we have a kind of a DAG representation, a relational database representation, what we've been thinking about is optimizations where we can drive the computations actually into more performant environments. So pandas is not super efficient, right? So you can think about things like, okay, can we do some of this computation in, for example, DuckDB, in an actual relational database? And that would make it much more performant as well. So I think by having the relational database representation, right, this DAG, there's a lot of opportunities for making it even faster, right? Because we can control that. So I think that's maybe helps with that.
Yeah. I think that that's a quite interesting idea. Okay, yeah, Sebastian is advertising a position at UVA. It's not relevant to the talk.
We're hiring. Let us know.
Yeah, but actually Gia has a question, so.
Thank you, Nadia. Thanks, Paul, for the great inspiring talk. I was wondering, is a lot of work that you've been doing, right, is related to structured data, so database tables. And now when people say or advertise work that they have been doing on machine learning, usually they show examples of machine learning on, developed for processing unstructured data like natural language, text, images, right? I was wondering, well, what would be the extra steps to go if we want to do similar things that you have been doing for structured data, if we want to do something as well for unstructured text or images?
So I think we actually do have a whole other line of work in the lab that is dealing with a lot of unstructured data, videos, natural language. And I think for something like ML Inspect, right, you have the same pre-processing pipelines that I talked about for some of these when we were talking about ML Inspect. So for example, we just showed one example where we used word embeddings to encode a particular feature. Now that's kind of a very simple example, but what we see is that the same approaches that you do to pre-processing, like if you're going to build a sequence-to-sequence model, for example, you have to do a lot of pre-processing of the natural language text if you're building a machine learning model for NLP. So the same kinds of techniques, you're doing a lot of data munging apply, right, in that domain. I think we also have an example in the image domain where you're also doing these feature mappings or these extractions. So the data processing pipelines still apply. I think the other thing to say on the work of what I see is really an interesting kind of combination, if you look at the knowledge graph space, of people looking at building essentially tools that not only look at the structure in terms of the graph or the relation, but also starting to look at the attributes, the actual attributes information. So I think corpora or tools that look at those combinations are super interesting. And we've done a couple pieces of work in that area.
Thanks for the answer. It's very interesting. I will definitely go and take a look.
All right, so yeah, in the interest of time, we need to move on to our first research talk. But Paul, thanks again for the great talk. And of course, if anybody is interested, you can continue the discussion offline with Paul and the other speakers today.